Hey, good afternoon and welcome back. And so in video 3, what we're going to be doing is calculating and plotting our pressure and volume isotherms with for water, as what we're looking at as a material, using the SRK cubic equation of state. And so we're going to be having an array of isotherms and wanting to see what happens for both the pressure and the volume at each respective temperature for water as we move through. And so let's go ahead and move forward with that now. And so what we're going to do is first we need to go ahead and grab the tools that we're going to need for the critical properties of water. And thankfully we can grab the files that have already been uploaded elsewhere. So we're going to upload it into our co-laboratory here. And so what it's doing right now is it's going to be downloading it. And so this is what we need. We're going to be able to need these tools, and it's going to already have in it the properties of water and various states and at critical properties that water shows, including values like the eccentricity factor and things like that we'll need. So then, moving forward, what we're going to end up needing is we're going to be dealing with arrays, and so we're going to need to use NumPy. We're going to be plotting, so we're going to have to bring in tools for plotting, as well as using the tools from what we've just uploaded into our folder here. And so we're going to go ahead and put all of that in now. And so let's go ahead, and what we're doing here is grabbing what we've just uploaded. And then next is let's go ahead and grab those tools. I'm going to type it out as CHE, so I have to type it in every time. For NumPy as NP. Then this is going to be for plotting purposes. I want to import make subplots. And then for templating purposes, for our background, it'd be nicer if it's black, and so it's just easier to visualize everything on it. So let's go ahead and set our template now to, let's go ahead and make it dark. And because we're dealing with gases, we always have our R as our constant, so let's just go ahead and define that as a variable now. We'll be using it later. Before I forget, just import all of that. Okay, great. So now before we start moving forward next, we just need to deal a little bit with the equation of state. And so again, as we spoke about in the last video, after Van der Waals made his groundbreaking discovery with the cubic equation of state, people came along since and added additional parameters to make things even more accurate with respect to how gases change in their behavior depending on the pressure and the temperature and the volume that they're under. And so here we're going to have A as dependent on as a function of temperature there, but we also have our B as our excluded volume, the space being taken up by each individual molecule. Here, the additional parameters that we see from Van der Waals, what he brought, but some additional parameters are epsilon and sigma. And then so we're going to be bringing those in as parameters. And so let's go ahead and start to get that defined here. And it's going to be in with respect to temperature. Now, our equation of state, we're going to end up we're using SRK, so let's just go ahead and define that now as our dictionary. And then next up, let's go ahead and start working through our different values. So we know that we're going to have A and B, but within that we're going to have, as we go down, what we'll see here is when we start looking at, well, what is A with respect to T? Well, A with respect to T, there's a couple different options here. One is temperature to critical point right here. We're not concerned with temperature to critical point. We want to know what is A with respect to T regardless of the temperature. We're looking at a whole array of temperatures. And so here we've got psi times this whole equation here. So let's just go ahead and some things that we know we'll need are psi. We know we're going to need omega there. I also see TR, and so let's go ahead and TR, I don't know why it's not flipping over. There we go. TR, what TR means is temperature, reduced temperature. Well, what is reduced temperature? If we look down here, reduced temperature is whatever specific temperature we're looking at divided by the temperature at the critical point. And so let's go ahead and define that. Temperature at the critical point. That's our TR. Let's see, what else do we have? We have alpha. Alpha is going to be something. And then we also have our epsilon and our sigma, as we saw up here. So we'll need to make sure we get those in. So let's just go ahead and get our epsilon and our sigma. Now, if we go down further, we'll be able to see what are the parameter assignments for each equation of state. Well, we're going to be dealing with van der Waals, and well, more specifically is SRK. But let's just go ahead and get van der Waals in there and our SRK when we're defining our parameters here with each respective dictionary. And so first we'll do van der Waals, and so the epsilon value for that is going to be 0. And then for SRK, the value for epsilon is also 0. Great. And then we're going to stick that in our dictionary that we're defining. This is the equation of state. Now let's move on to sigma. Sigma, again, is going to be, we'll start with van der Waals. And sigma for van der Waals also is 0. SRK, sigma for SRK is 1. Let's go ahead and get 1 in there. And then also put that in our equation of state dictionary. We don't want that there. There we go. Okay. Now the psi, well, what is psi? Psi for van der Waals is 27 divided by 64. And then for SRK, psi is 0.42748. Great. And then let's make sure everything's so good. Okay. Now 0.2748. Okay, we're going to put that into our equation of state dictionary. Omega, what is omega? Starting with van der Waals. Omega for van der Waals is 1/8. Now for SRK, omega is 0.08664. Put that in our dictionary. And then alpha, okay, so alpha for van der Waals is 1. It's nice and easy. However, when we get to SRK, we're going to find it's not as easy. Let's see here. So here we've got, for SRK, here we've got a little subscript saying, look down here, here's the whole equation. So the whole equation is going to be multiplied, well, it's going to be squared. So let's just go ahead and get that square out there to start. And then let's work our way through it. So 1 plus 0.48 plus 1.574 multiplied by omega. Well, omega is just the eccentricity factor which we already have a property for, and we're pulling that from our chemical tools that we've already uploaded. So we can just put that property in there, which is great. 0.176 multiplied by the eccentricity factor squared. Okay, and then that whole thing gets put in parentheses. Then we start a new parentheses. 1 minus the reduced temperature, and let's get the reduced temperature nope, not squared, to the 1/2. That would certainly make a difference. Okay, to the 1/2, and that is closing out that one. That parentheses is closing out that. So I believe we've got our bases covered. Okay. Let's bring this over a little bit, run out of some space there. Okay. Now, let's see, what do we have? So we've defined our epsilon or sigma or psi or omega or alpha. Okay, so now we are ready to define A with respect to temperature. So we brought in our psi, so let's go ahead and multiply psi times alpha. So we've got our alpha times, we've already defined R earlier as a constant, times critical temperature squared, and then this whole thing divided by the critical pressure. Now that is it for A. So now the other thing we have is B. B is the last parameter we have not defined. So now we've got omega times R times our critical temperature, all of that divided by our critical pressure. There we go. Okay, so now let's go ahead and return these values and calculate for P. So it's a good segue. So what we actually want to do next is calculate for our pressure, right? Because when we look at our cubic equation of state, that's what we're trying to calculate. We're trying to find what our pressure is given all of this. And so we're going to set our pressure as a function of volume with known temperatures. Again, we're dealing with an array of isotherms, and so the temperature is going to be staying constant. And with that constant temperature, we're going to set our pressure with respect to volume. So let's go ahead and get that in. Now we're defining this. Okay, we need to unpack the parameters that we've previously defined, which would be everything we just did above. Okay, and let's go ahead and now all we have to do is actually just return our equation here. So R times temperature divided by volume minus our excluded volume. Okay, and then this whole thing minus A divided by volume plus epsilon times our excluded volume, and then that times volume plus sigma times our excluded volume. There. Okay. See if that works. Okay. Now let's go ahead and see what happens when we, let's just set, let's say 1 cubic meter and at the freezing point. Okay, it still doesn't like, so I am missing something with what I'm doing here. Equation of state. And I have to find it down here. Is that what we're doing? Still doesn't like it. Keeps coming back to TR. Pressure at the critical point of temperature, or at the critical point of temperature. Critical point of temperature. One second. So the problem is, looking at here, it keeps telling me P is not defined, and that's true. I forgot to define P along the way here. So P, let's go ahead and define that now. And what we want our P is, we're looking for the properties of water, because that's the material we're working with here. So let's go ahead and get that in. There we go. So now we're pulling P as the chemical properties of water. That way, every time we have our P dot, temperature at the critical point or pressure at the critical point or anything like that, it has to be pulling from somewhere, which in this case now it's going to be pulling from the critical properties of water. So now we're going to rerun that, and still giving an issue. Float object not callable. Okay. So I've got a float object somewhere that's not callable. I'm saying alpha. Let's try and get that period in there. See what that does for us. Let's try this again. Try this again. Still doesn't like it. Oh, I've got to, let's see. There it is. I never defined alpha and never stuck it in my dictionary. Let's try that. Ugh. Now what? Forgot to put a multiplication right there. Let's try that. Let's try that. Ah, finally. There we go. All right, not one thing wrong with coding. Otherwise, the computer is very angry. Okay, so now we've got our temperature, our pressure. This is our pressure value. When our volume is 1 cubic meter, when our temperature is 273. Now let's just make sure our calculations look correct, because if we make our volume substantially smaller, even if we keep our temperature the same, the pressure should be higher. Yeah, and it is. Okay. And then let's go ahead and keep it, put it back to that. But we should also see the pressure go higher. Let's do, I don't know, 750. When our temperature goes higher. And there we go. We see it rise as well. Okay. Now we've got all of that. All of that looks good. Now our last thing is just to go ahead and plot out everything that we've coded so far and defined and calculated for pressure. So our volume, it's going to be on a logarithmic scale. So let's go ahead and get that in now. We're using an array of values. So we need to get the NP in there. And then Now, something that we want to consider as we're plotting this is our starting point and our ending point. Now, with our starting point, we can't have our denominator at 0 because then we have an infinite value. It's undefined. It's not going to give us anything to work with. So we have to make sure that our denominator is greater than 0. And since B is excluded volume because of molecules taking up space, B can't be greater than the volume because the molecules can't physically take up more space than the actual container that they're in. That doesn't make any sense. And so let's go ahead and have our starting increment as B, just 1% greater than B as our excluded volume. So let's go ahead and multiply this by B. Now in so doing, we're going to need to, let's just go ahead and bring B back down here. And we've already defined it right here. Just go ahead and grab that. Now, I would leave omega in if we were going to be pulling from different equations of states, but since we're just in this video dealing with the SRK equation of state, let's just go ahead and already preset our omega specifically for that. So we'll get that there. Okay. Now our starting point is going to be 1% greater than B. Now our next point, another thing to consider is that because we're doing a logarithmic scale, each of these start and stop values are 10 to whatever value we're putting in, and so it's going to grow rather fast. And then another thing is a lot of the activity we're going to be looking for that's going to be interesting to us is going to be happening under smaller volume situations where the pressure is going to be a bit higher because the volume is quite a bit smaller. And so let's go ahead and start with a smaller value for our logarithmic scale and for volume, and because that's going to end up being 10 to the negative 2 for our volume as our ending point. And then let's get a whole lot of data points in between there. Now our plotting figure, make it subplots. Okay, now the next thing is plotting the temperature. We don't want just one temperature. We would like to see what the pressure and volume, how they look and how they change based off a whole array of isotherms. So we want to be able to see just what happens based off a whole array of temperatures as water moves from being really cold to really hot, and see what that does to the pressure and the volume. So let's go ahead and make a whole for loop instead of just one temperature value. So let's start near the freezing point. Let's get it really nice and warm, and we'll move at 25 Kelvin increments. And then what is it that we're concerned with? Well, we would like to know the pressure at each respective temperature there. So when temperature is 275, when it's 300, so on and so forth, it keeps running through and telling us what the pressure is at each temperature there. So we are dealing with our volume and our temperature. And then, let's see, what else would we like to add? Well, we're going to need to get some data points for it to actually calculate. So our volume is going to be our independent variable because our pressure is a function of our independent variable, which is volume here. So X is V, Y is our pressure, mode, let's do lines, and then the naming the graph. Let's go ahead and T equals, so now because we're going to be doing a for loop, we'd like to see, so what it's going to do is whatever particular loop it's on, it'll rename that with those brackets here that I just inserted. Kelvin. Okay. And now let's go ahead and make sure our axes are going to accurately reflect our logarithmic scale that we're dealing with. So we're going to need to set this to logarithm for the X axis, and then we're going to need to set what we'd like to see our range for the y-axis to be. So let's go ahead and do really low pressures. Make sure we're getting a lot of values in there. And then let's do high pressures. Make sure we're getting a lot of that value in. So let's go ahead and run this, see what it gives us. All right. So what we see here, which is incredible, is it's running through each isotherm here, 275 all the way down to 700, well, all the way down to 800, there's 775, and showing us what happens for the pressure with respect to volume for each isotherm. So if we keep zooming in here, we're going to be able to see all of this incredible activity happening. And so this right here is having calculated and plotted our isotherms, our array of isotherms for water using the SRK equation of state. Thank you.